Alright, this is the final run of our Scrambler before we disassemble it. Wanted to show everybody how it worked. Pretty cool. We have our car here. It stopped using kind of the traditional wing nut. As the wheels spun, the wing nut moved, and when the wing nut hit the end of the shaft, it stopped it. So it would spin and spin harder again, and there you see it's getting closer. It's gonna hit, and it stopped. So that was pretty cool, but we got this thing to go pretty fast at a relatively high velocity that it would skid. So what we needed to do is we needed some kind of energy absorption device, and we did that with some rubber bands. Rubber bands also that were connected to a threaded rod on the back. This worked really well, actually. We were able to absorb the energy, most of it, before we had to brake. So we did a little skidding. So that's our vehicle. We used kind of skateboard rollerblade wheels, and that worked really good too. It was very hard to try to straighten this threaded rod. It was kind of crazy. But I'm going to turn this over, talk a little bit about our launch system here. If you can kind of see it, we had to fit within the dimensions of 1 meter high, 1 meter long, and 0.75 meters in width. So we tried to maximize all of that. We used a pulley system. As you can see, here's pulleys. We used wood pulleys, actually 2 pulleys. If I get a little closer here, you can see the pulley. So we use a larger pulley and then a smaller pulley to give us a little more speed. We weren't able to actually check if that worked really well. We should have actually did some kind of acceleration graph. We didn't have time to do that. There's the main drive pulley. I guess that's what we were calling it. And so the string, as you can see, kind of makes a triangle loop from the main drive pulley down to this lower pulley. Let's see if I can get a shot of it underneath. I move down. There's the draw. So that's the lower pulley connected to the drive up there, and then we went to the back pulley. So we have this kind of triangular loop. One of the things we found out is that we were worried about slippage on these plastic acetal, what they call pulleys. We put some rubber bands underneath. I don't know if you can see it very closely, but there's rubber bands underneath to give us some friction on that string. We might have used another method. This worked pretty good. Yeah, as you can see, keeping the whole system together is a turnbuckle. One of the things we kind of discovered is that if we had too much tension, we actually lost a lot of energy. So speaking of energy, how did this thing turn? Well, the competition said that we needed to use a maximum of 2 kilograms of weight to as a falling mass to provide the energy. And so we used some threaded rod. And there's the weight on the back. I don't know if this is making it good. So there's the weight attached with 2 strings on each side, and they go up to the shaft. where the pulleys are connected. I'm gonna stop the video and wind it up. Or maybe I can kind of wind it to see a little bit, just so you can see how it. So as you wind it, the weight moves up. Alright, so I'm going to wind it up. Here we are again. Oh, one of the cool things I wanted to show everybody about the Scrambler is the way the car actually is accelerated. So I'm moving back, or I'm lifting the weight at this time. So the car is accelerated by this frog tape container, top, lid. It's kind of like a Tupperware container. So we moved it back, and as it moved forward and made its way to the forward pulley, it was supposed to be going faster and faster due to the different size of drive pulleys. And at the very end, it got this really cool kick. I don't know if you can see that. As it dropped, it went boom, and it kicked it, this last kick of energy. So that was kind of cool. And you can see how we attached the this lead with two eye hooks and a kind of like a standoff coupler that we got from Home Depot. And that worked out really good. Okay, I'm going to stop the video again and wind this thing back with the weight, and we'll watch it go. Alright, here we are, ready for its final run, for its deconstructed, disassembled, torn apart, tear, sadness. I'm going to look at the back and show the weight again. There's the weight. I'm trying to point at it with my finger. The weight, this rod. So we've wound the string connected to the weight about 2 times on this larger pulley, only 1 time on the smaller pulley, and then the shaft, it's connected to the shaft, and so that gets some kind of fractional turn on the shaft. So most of the time is spent on the larger pulley, so the weight drops very far without the frog tape container moving much initially. And then when it gets to the small pulley, we have a very large movement in the frog tape compared to the frog tape container compared to the actual falling distance. So we're not sure if this was the best way to go because we didn't do an acceleration graph, but theoretically it sounded good. Here's our little activation mechanism. It's being held, if you can see it, it's being held by this piece of aluminum, which is connected. Let me see if I can move around. So that piece of aluminum is connected to a piece of wood. This wood is counterbalancing the 2 kilogram weight almost exactly. So it's counterbalancing, and it takes just a small push to activate it. And so with that said, let's activate it and see this thing go. Okay, I'm gonna push it, reaching as far away as I can. Oh! Go, baby, go! And there she goes. Moving, moving, moving. How far did she go? Well, we marked some lines here on the pavement. There was our 9-meter mark. There was our 10-meter mark, our 11-meter mark, our 12-meter mark, our 13-meter mark. And there it went, a little bit past 13 meters. I'm pretty sure we got to go a little farther before, but that's one of the keys that you want to somehow be able to impart the same amount of energy every time. That way we were able to give a certain rubber band turn. However, that was it. And that's our scrambler. Thanks for watching.